So we need to understand what the future holds, and we are relying on these models. As we said, they are not perfect, but they have a lot of information, and that can be verified for the past, right? So here we are showing cumulative total anthropogenic CO2 from 1870 in gigatons carbon. That is mega, giga, and that's 10 to the 9 tons of carbon. So carbon accumulates, as we said, because it has long residence time. And there are various colors here which corresponds to various scenarios for the future. So when you go into 2100, for example, which is shown here, end of the 21st century, you can make various scenarios of population, technology, renewable energy, carbon capture, and so on, and say we will limit the radiative imbalance to a fairly benign 2.6 watts per meter squared, or 4.5, and almost business as usual where it would reach 8.5 watts per meter squared. And you look at the models for the historic period here, going from something like 1870 to 2010. So this black line is what we know happened. So models are able to reproduce the past fairly well given the greenhouse gas emissions that we have, which means they are fairly reliable. So you believe in that, and you add future scenarios, and you produce various projections. Okay, so you can see that 2.5 RCP is representative concentration pathways of greenhouse gases in terms of CO2 equivalent, for example, because you have to convert all the greenhouse gases into CO2 equivalent, which is not a hard thing to do. You can see that by 2100, RCP 2.6 would give you a warming of less than 2 degrees. We looked at the impact of 2 degrees C warming, which are pretty bad, but given the CO2 we have already put in, a couple of trillion tons of carbon, and the trajectory of emission we are on, that is not a bad target to hit. But if you increase it to 4.5, you reach up to 2.5, 3 degrees, and 6.5 and 8 will take you, as RCP 8.5 will take you to a very, very warm temperature, which is going to be disaster in many ways. Okay, so these are the ranges of CO2 change shown here in colors, going from the RCP range, which is in this magenta-ish color. Increase of 1% per year is going to give you this, and increase of range of this 1% per year is over here. Okay, that's the mean and that's the range. Okay, so these are the cumulative total anthropogenic CO2 emissions. So that's gigaton CO2, and this is gigaton carbon. Okay, there's just a multiplication factor of 3.7 or so to go between carbon and CO2. Okay, so this shows that the accumulated carbon and the warming are almost linearly related. So in some sense, you can take the warming you want to aim for and look at how much CO2 is left in terms of what we have accumulated already and what we will get if we go there. Then you can see, using our emission rates, how much more we can, how long it will take for us to reach there. I hope you understood it. If the warming is linear, each additional gigaton of carbon will give you a certain amount of warming. Then you can aim for a maximum warming of, let's say, 2 degrees and figure out how much carbon we are allowed to emit to remain within that range. And we know how much we are emitting per year, so we can figure out how many years approximately we have left. It's not a very good idea to say that's the deadline and the world will come to an end when that happens, but nonetheless, it's a good number to have, right? So the projections also include many details, which we will not get into here, but you can look up the IPCC reports. This is just an example of soil moisture in the top 10 centimeter layer compared the period of 2080 to 2099, end of the century, is being compared to the base period of 1980 to 1999. And you can see that there are many places where soil moisture will get reduced tremendously in terms of percentages. So soil will get desiccated. So California here is a hot spot. This is where the wildfires are very common now, and drought has become quite persistent. So this is not good news for that. But there are also uncertainties, because Sahara here, for example, is showing a increase in soil moisture. Okay, so there is some indication that there may be increased rainfall there with warming. And there is evidence that about 9,000 years ago to 6,000 years ago, Sahara was much greener because the orbital changes had created a monsoon over there, and civilizations expanded away from the Nile, and then when the monsoons disappeared about 6,000 years or so, they all collapsed towards the Nile, and many went extinct, right? Like the Vikings who colonized Greenland and went extinct during the medieval warming. India here is showing also some increase in soil moisture, but the models are not very accurate in every region. As we said, for the global mean, they do very well, but when you go to local scales, they are not supremely accurate. So we have to be careful about that. Nonetheless, we can use these model outputs in terms of their details. For example, with this, you can say what kind of crops will grow, especially when you consider with the warming. Okay, you take the warming, you take the change in soil moisture, and you try to decide whether the crops that are grown now will still be able to be grown in the future, or you have to switch to some other crop. Or if Siberia gets warmer and moister and becomes the breadbasket of the world. Okay, higher latitudes get wetter, and these latitudes are getting drier in terms of soil moisture, right? So take all that together and look at the probability of the range of warming by 2100. Okay, if you look at the business as usual with confidence intervals of 80%, 50%, and 50% with carbon feedbacks, this is kind of a detail where the models account for how vegetation change affects climate. Climate affects vegetation, vegetation change affects carbon, and that carbon then affects climate as well. So those kind of feedbacks can be included. Nonetheless, these various scenarios tell you that the warming depends on, for example, including carbon feedback, increases the warming and the tail. So the extreme temperatures can get as warm as 8 degrees with respect to the base period, whereas without carbon feedbacks that is lower. So the 80% probability is here, and confidence interval, and I hope I'm right about that. I will check and correct it next time. Okay. Nonetheless, these are considered dangerous ranges, catastrophic ranges, and here is where we will get into existential crises. And these are what are proposed in the book. The book proposes 10 solutions which will pull us out of this dangerous zone and bring us into this milder warming, as well as a reduced danger of climate change. Okay, so the probabilities are shown here. So you can see that with these 10 solutions, with almost 100% assurance, we can say that we can keep the warming to below about 1.5 degrees. Okay, so let's quickly look at what CI stands for. No need to go too far without knowing what that is. Here we are. So CI is carbon intensity. So how the energy production is for this scenario, and BL is the baseline. So baseline is something like 2005, for example, and with respect to that baseline, you choose futures where the economies, GDPs, energy production, everything will have carbon intensity. So if you reduce fossil fuel burning and increase renewables as well as maybe include carbon capture, then you will reduce carbon intensity. So baselines and carbon intensities, but the story is the same, that with sensible solutions we can get out of this catastrophic and existential and dangerous levels and keep the warming to a manageable level. So it is essentially about, as the cliche goes, managing the unavoidable and avoiding the unmanageable. Okay, that's the idea of seeking solutions to global warming, climate change, and climate disruption.